Hi, I'm Tory Bruno. I've been a rocket scientist for 40 years, and I got to tell you that every single day has been an adventure. I have gotten the opportunity to do just amazing things. I have slept on a torpedo. I have shot a bullet out of the sky with another bullet. I have stood in the middle of Armageddon with all of its terrifying and awesome power. But I have also sent a spacecraft into orbit around the sun, the fastest human object in the universe, flying directly through the literal atmosphere of the sun. There is no career like a career spent in service to this great nation, service to the awesome cause of exploration, and service to the great calling of human dignity around this planet. And now, on the burn sequence, I'm going to pull that curtain back a little bit and let you look inside. So welcome to our show, and welcome to the burn sequence. Today we have a super fun guest. We're going to geek out on rocket science and engineering. I have got the legendary Destin Sandlin with me.
Are these bad legends?
No, these are good legends. One of the great communicators of STEM, with a wonderful YouTube channel. We got like 12 million subscribers
it's
now.
11 something, I think.
Oh my gosh.
It's a lot.
Well, I think you are probably the best STEM communicator I've ever seen.
Well, I appreciate that, Tory. I enjoy just sharing things I'm curious about, and I feel really honored that I get to do that. It's a really cool thing.
Well, it's awesome.
Almost as fun as rocket science.
Almost. So welcome to the burn sequence.
Thank you so much. Glad to be here.
All right, I got questions.
Okay.
Are you ready? All right. By the way, I don't know if everyone knows, you're a real engineer, no kidding. Mechanical engineer, aerospace engineer. You work for the U.S. Army in operational test. So, you got the whole deal.
Oh, I appreciate that. No, it's interesting because I was doing that for years, and then at some point it made sense to do the YouTube thing with a little more attention to that.
Yeah.
And so that's what I started doing.
Well, I'm glad you did.
Yeah.
And apparently 12 million other people are too.
It's fun. It's fun.
All right, so we're going to start with some easy ones.
Okay.
So, how'd you get started? How'd you get inspired to want to do the YouTube channel?
YouTube stuff?
Yeah.
Oh, okay. That's fun. So I was on the test range, and I made a thing. It was, a rocket corner reflector. Well, excuse me, I'm conflating two things. A corner reflector for radar.
Yep.
So we were working on a detection system, and I put a corner reflector at the end of a rocket, and we shot it down a rope.
Oh, cool.
It's pretty cool. And so
Yeah.
we were training radar how to detect things.
Sure.
And
the corner reflector is like to have a known reflective source that you can calibrate to. Is that the idea?
Exactly.
Okay.
So this was back in the early 2000s, and a lot of people, we were trying to detect rocket-propelled grenades is what we were doing.
Yep.
And there was an outfit over on the Arsenal, some really smart guys in a group over there. They were flying this really big radar cross-section. They were using a hemisphere down a rope. But the problem is there was a lot of mass to that.
Oh, yeah.
And I thought, well, if you used a corner reflector, you would get a more significant return.
Right.
And if you calculate one leg of the tetrahedral there, depending on the frequency, you can get a known RCS, radar cross section.
Okay, clever.
And the drag coefficient would be way lower.
Sure.
And so I was able to get up into faster velocities.
Yeah.
So I did that.
Yep.
And then went home, and I had a fire that needed to be burned in the yard. It was a big bonfire.
Yeah.
I thought, I'm shooting rockets down ropes on the Arsenal.
Okay.
I should just shoot fireworks down ropes at home. And that's what I did. I lit a bonfire with rockets. I made the first YouTube video just to show.
I don't know if I've seen that one. Is that still on your channel?
It is. It's very, very old.
Okay.
Not many people have seen it, but how to light a bonfire with rockets was my first video on YouTube. It's pretty fun. And
so this guy back here, you think you could light a bonfire with one of those?
with a Centaur, you could probably light a lot of things with a Centaur, but I don't think that's typically. Well, I guess coming out the business end there, yeah. That's a pretty. This is a Centaur 5 behind this, right?
Yes. Yeah.
Okay, it's really cool. Have you ever done a burn sequence here in the plant?
You're the first one.
Really?
Yeah, yeah.
I'm very honored.
Well, it seemed only fitting.
I appreciate that.
So that's how you got started. What put it in your head, though? Why did you want to become a STEM educator?
I didn't. I just still don't think of myself as a YouTuber. I think of myself as an engineer. I know that sounds silly, but genuinely, I feel like an engineer. And then the YouTube thing, I just really like making videos and just telling stories about what I'm learning. And it just kind of happened. And so it's kind of a thing I kind of have to do. I don't know. It's a weird thing. It's almost like it caught me.
Yeah.
Does that make any sense?
Interesting.
Yeah. So that's why when I get to come into a factory like this and I smell the cutting fluid, and I see all the remove before flight tags, I get very excited because this feels like home.
Of course.
Yeah, it's awesome. And so it's a strange thing, but I love making YouTube videos, and my favorite thing about it is that it opens up doors, and people have been very kind to me, and they trust me, and they say, well, because Destin has not botched up some of the other stuff, maybe he won't botch my thing up. And so they let me come do things. Like the tour today you gave me earlier. Thank you so much.
Oh, it's my pleasure.
It was awesome.
Well, people trust you because you're trustworthy.
Thank you. Yeah, and I think that's a thing you earn over time.
Mm-hmm.
And I think you have a reputation for being a person that knows what they're talking about. And that's something that you develop over many, many, many years, but can go away in a snap of a finger, can't it?
Yeah. Yes. It takes forever to build trust and confidence. It takes a minute to break it, and then, half of forever to get it back if you ever can.
Yeah.
Integrity is important in this work, I think.
It is. It is. And what's so interesting about what you're doing, like, for example, the Centaur behind you, it's a pressure vessel. Everything about it has to, like, if there's one little place anywhere that it can't hold pressure, the whole thing fails. And so you know that it's going to fly because of the integrity of the hull. And so, and you're right, integrity is important. Echoing what you said.
Well, I assume you know this, but you just have a talent for taking complicated technical topics and making them easily understood, and not just interesting for other engineers and nerds like me, but people who don't have a technical background. You're able to explain it to them. It's kind of like a superpower. What's your secret?
Well, you have it too. You were just explaining complex grain structure to me, and what I've noticed that you do. This is what I've noticed you do. You start at the least common denominator. Is that the greatest common denominator? You know what I'm trying to say.
Yeah.
You start at a common baseline that we agree on, and then you build off of that. So you find where I'm at, and whatever I do understand, then you start working from there. And that's all I do. It's like climbing a mountain with someone.
Yeah.
And so I do that and just slowly ramp it up. And when my grandmother was around, I used to do this thing called the granny test.
The granny test.
The granny test.
Okay.
I would play a video for Granny.
Yeah.
And I would see the point that I lost her. And then I would back up, like, okay, I need to fix it there.
That's brilliant.
Yeah. But you're very good at this as well.
Oh, thank you. I try and think about who I'm talking to, and just sort of put yourself in their boots, because I think in our world, technical people, we're so into the technology or into the topic we're trying to describe that we're, in a lot of ways, it's easy for us just to talk to ourselves or to an audience that we imagine understands it as well as we do. And we forget, no, you're not talking to yourself. This is not an inner dialogue. You're actually talking to this other person, and if you can just remember who they are and what they're going to hear, it goes a lot better.
I agree. Another thing I do, I don't know if it's just the way I was raised, but I'm just very honest about my ignorance. And so a lot of times, I think on the internet, people that want to explain things feel like they have to be the knower of things and they explain it. For me, it's kind of a cheat code. I get to ask the question and genuinely not know the answer. So a lot of times I'm just talking to the expert, and the expert knows the answer, and I just get to ask. And so you taught me so much today about material science. It was unreal. It's fascinating. So I think not feeling like you have to be embarrassed because you don't know something is something that I've found a lot of people give me grace with that.
nobody can know everything about everything. And especially in our world, in world of technology and engineering, um, it's just literally impossible. And so yeah, I'm with you. I'm not sure I understand why people are embarrassed not to be an expert in every field of science. It's literally impossible.
It is impossible, but you are very close to an expert in the aerospace realm. I mean, you're. I'll let you in on a secret. One thing I started doing with you early on when we started talking is I started asking questions and just probing and seeing like, okay, where's the limit of Tory's knowledge on this particular subject? And then I would go to where I thought it was, but you just kept knowing stuff. So I kept going a little bit further and further. And then finally you get to a place and you'd be like, I don't know, but I'll get you the answer, which is a great answer.
Yeah.
So
Well, you never want somebody to make it up.
Right.
And there's no shame in that.
Right. Yeah. You're a bit of a unicorn.
I've been really, I would say, really just lucky in my career. I've gotten to work on so many different projects. And in our world, if you do 2 or 3 systems across a career, you've done a lot. And that's pretty normal. And I just kept getting moved around and challenged with different things. I've done 3 dozen different systems.
Really?
In lots of different domains, all of them aerospace, of course, most of them in rocketry. And
Forgive me for not knowing this. What was your degree in at Cal Poly?
mechanical engineering.
Mechanical?
Yeah.
Okay.
And so I started in rocketry with Lockheed, and I did hypersonics, and I did, of course, rockets, and I did a lot of different subsystems in the rockets, because early in, I got involved in a major problem investigation, and it was a turning point for my career. After that, I always had a day job, but during the day job, if there was something that had blown up or was broken or whatever was a crisis, I would get yanked out and parachuted in to go work it. And when you work problems, you learn 10 times faster than when you're doing routine design or routine production. And then you kind of get stuck that way. You're like branded. Oh, we need a task force or a Tiger team. You get pulled out. And so the next thing I knew, had just worked all these different things.
So I've heard the term Tiger team. I've never been on one. I've also heard it called a red team.
Yeah, same thing.
So you've been on those. I've never done that.
Oh, I did that 20 years straight, where I just went from one to the other, to the other, to the other.
Do you think you were selected for those because of technical prowess or because of communication skills?
Both.
Okay.
Yeah. So I'll tell you a little secret. I didn't want to go into management.
Okay.
Had no interest in it. I just wanted to be a rocket scientist, and that's all I did for about the first solid 10 years. And pretty early on in that is when this major thing had happened. This was a nuclear weapon system, brand new missile. We're still in the Cold War. It was a big frickin' deal when in its first sort of operational test, it cartwheeled and exploded.
That's not a good thing.
Not a good thing. And, everybody got dragged into a room, the whole program. And so, okay, you guys, every one of you guys who's responsible for a piece of hardware on this rocket that could have been involved, you will go and work on it all day and into the evening, and then you're going to report out tomorrow morning at 06:30, And so I go off, and I'm going through the data, and I go, shit, I've got it.
What?
I figured it out.
You
I figured it out, so I knew what it was.
Was it something you did?
No, thank goodness. It wasn't my fault. But I stayed all night because I knew, I was a junior engineer, and all the senior guys would be reporting out in the morning, and I couldn't just show up and say, hey, I figured it out. I had to be able to prove it. And probably, dark 30 in the morning, my boss showed up, and I went into his office. I said, hey, Don, I figured it out. And he goes, figured what out? And I go, the flight failure. I know what the cause was. He said, all right, kid, let me see what you got. And this is the old days. People were smoking cigars in the office, and they were kind of grizzled old. So I go in there and I show him. He goes, shoot, I'm cleaning this up a little bit. Shoot, you do have it. And so he dragged me to the meeting, He was supposed to brief. He made me brief. First public presentation I ever gave
Wow.
was to a room with about 300 people in it and an admiral. And I kind of bumbled through, and they went, "Oh my God, he's got it." And then I spent the next probably year of my life without a day off, while everybody else, every man, woman, and child on the program did the same thing, designing fixes for that, getting them qualified, and getting that system back into service, because it was about nuclear deterrence in the Cold War.
Right.
That was a turning point for my career. From that point forward, I just worked problem after problem. And when I finally caved in and went into leadership, it would just be that. It would be a broken department or a broken program or whatever the problem was. And it was very lucky. I mean, I just happened to be in the right place at the right time to be afforded a trajectory that had me working on so many different things and learning so much about it.
So you were transplanted into areas that were in transition.
Yes.
That,
Often in development, because that's when you break things.
okay.
And a problem that couldn't be fixed. People were just stuck. And when you get something like that, senior leadership will go, okay, we need new eyes. So we're going to take someone who can run a task team, tiger team, red team, task force. We're going to let them pull talent from all over the company and form a special team to go in and try and solve it. So that's what that means.
Interesting.
And I got tagged to just lead those one after the other.
That's fun.
It's super fun. And part of the secret, by the way, since you mentioned that, is you're just having a ball, and you've done a bunch of these now, so you're good at it. You got your favorite team, but you can't look like it's too much fun, because everybody else is dying, and you can't be walking around with a big smile enjoying the nightmare.
I see. Interesting. And so, is there another component of that when you get dropped into an area like that where things are kind of messed up? Do you get a little bit of extra forgiveness because it's already messed up?
Yeah.
You can only
make it better.
Okay.
And in terms of your career trajectory in our world, when we manage by exception is what we call it. So you're managing the problems. The things that are going right in a program don't get much attention. That's not always healthy, by the way, but that's just how it's done. So if you're working a big, nasty problem, everybody's watching. If you screw it up, make it worse, you're done. But if you help, then everyone knows that and you're appreciated for it.
That's nice. That's awesome.
So when young engineers ask me for advice, I go, well, look around your department for the awful house on fire furball that everybody else is fleeing. And if you think you can help, volunteer.
Interesting. Okay. I've never thought about that. So run to the fire.
Run to the fire.
Interesting.
Well,
okay.
You're going to have the biggest impact. We don't do this work for money or for prestige. You're doing this work because it's important to your nation. And so you want to have the biggest contribution you can make.
So were you with Lockheed all the way up until...
Yeah, till I came here.
Okay. Gotcha. Interesting.
You're interviewing me.
I am. That's kind of what I do.
See how good he is at this? Oh my gosh. All right, well, I got a question I'm going to ask.
Okay, but I do have a technical question for you before we cut the mics off. We don't have to do it now. We can do it whenever you want.
All right.
You want to do it now?
Anytime you want.
Okay. Here's a question I have for you. So I have read a little bit about this, but I haven't probed the depths of this. I want to know, I know there's some term for the state of an orbit of a satellite.
Sure.
And I think it's 6 terms, I think?
Yes, 6 parameters.
6 parameters.
Define an orbital state.
Is it called an orbital state?
Yes.
It's called the state parameters. Is that right? Okay.
Yeah. It's not a state parameter in the way you might think of it in fluid dynamics, which is an immutable property of the system. This is more like how you define an orbit and where you are in it.
Okay, so there's 2 things there. There's how you define the orbit and where you are in it. Those are 2 different things? Okay, so if I had to guess, I would say 3 of those terms are defining the orbit, and 3 of them are where you are. Is that true?
Yeah, I mean, I think about it this way. So starting with 2 things, Everything's in orbit all the time.
Everything is in orbit all the time.
All the time. You and
Okay.
I are orbiting the sun.
Okay.
You
got
and
it.
I are suborbiting the Earth.
Okay.
We're in motion right now, hundreds of miles an hour.
Right.
Sun's orbiting the galactic center, so on. So everything's in orbit, and all orbits are ellipses.
Keplerian.
Exactly.
Yeah. So Johannes Kepler,
You got it.
really smart guy.
German, 16th century,
Okay.
contemporary of Queen Elizabeth, so you can put it in context.
I didn't know
Mathematician.
that. Okay.
And so Kepler came up with this. He came up with the way to define orbits, laws of how orbits behave. And so we're going to, in terms of these 6 orbital parameters, we're going to do like 3 things. We're going to describe the shape of the orbit and how big it is. That's one thing.
How big it is.
Yeah.
So that's from whatever I'm orbiting around,
Yeah.
the distance to that.
Is it an ellipse? Is it a long skinny ellipse?
Oh,
Is it a nice like circular ellipse? Because a circle is a special case of an ellipse.
so is this the eccentricity? Is that what this is?
Yes, yeah.
Okay.
We'll come to that.
Okay.
So how big is it? What shape is it?
Okay.
That's one thing. I'm going to do this. We're going to do this at 80,000 foot level.
Okay.
I should say the 500 mile level, so we're in orbit.
That's right.
And then I'll drill down into the 6 parameters.
Mm-hmm.
And then how is it oriented in space? Now that we know if it's a circle or a skinny ellipse or a fat ellipse, how's it, pretend my hand is an elliptical orbital plane, so an orbit. Is it like this? Is it like that? Is
So
it
you're
like
doing
that?
you're cutting the Earth in half at the equator for one of those hand motions.
Yes,
You're tilting it
yes,
for one of the other ones. Doing this if it's audio
Right.
here, and then okay, got it. So you're
You got
finding
it.
the plane of the angle there.
So what's the shape? How's it oriented? And then finally, at any moment in time, where are you on it?
Okay.
All right, so the shape. And you went there right away. So you know it's an ellipse. And what we want to define is first, how big is it? So we take, I'm going to call it different. I'm going to come back to Kepler in a minute, but I'm going to talk about sort of the diameter of the long axis, the length of the long axis of an ellipse.
Okay.
So if you can picture that in your mind. And in orbital talk, in Kepler talk, for a Renaissance era German dude who wrote it in Latin, and we're working with the English translation.
Okay.
All right. So that's, you have the major axis. That's that long diameter.
And if I were to draw an ellipse on a piece of paper, it would be the tip to the tip.
You got it. Tip to
Okay.
tip.
Okay.
And then we want to take the radius, so we call that the semi-major axis, because semi is half. So half of that tip to tip,
Okay.
right? That's the semi-major axis.
Semi-major axis, meaning the long side. Okay.
Half of the long side.
Got it.
Semi is half.
Got it.
Okay, so that's that, and it's a number. It's so many kilometers. So now we know how big it is. Now we just need to know, is it skinny like a cigar? Is it nice and round like a donut? And that's the eccentricity. So now we know it's an ellipse, and we know whether it's long and skinny, or whether it's a donut, or where it is in between. So now we know the shape and size of the ellipse. That was the first thing.
So you said that's one parameter. That was one term that we
It's actually 2. So if we're going to drop into the 6, you would define the semi-major axis
Okay.
and the eccentricity.
Okay.
Those are 2 of the 6.
Okay.
That tells you the shape and size of the orbit.
Got it. Okay.
Now we want to know how it's oriented.
Got it.
That's where it gets interesting.
Okay.
There's a whole bunch more parameters there.
So let's say we're going around the equator.
Yep.
So we're just an equatorial orbit,
Yeah.
and we'll say our eccentricity is 0. We're
So it's a circular orbit
It's a
at the equator.
okay.
That would be the next parameter, which is inclination. And if we're sitting at the equator, the inclination is 0 degrees.
Got it.
If we're orbiting the North and South Pole, the inclination is 90 degrees.
Easy. Okay.
Okay, and everything in between. So now we've got 3 of the 6. That's okay. So here we are. Here's my orbit again. I don't know if I'm on camera. Here's
Yeah,
my
yeah.
orbit again.
Yeah.
So the next thing we want to know is, well, is it here or here or here?
Oh, okay. So let me see if I can describe this for the podcast. So if I'm looking directly, I'm cutting the Earth in half. my orbital inclination is 0. If I'm going to the poles, the orbital inclination is 90. But if let's say I'm at a 45-degree angle.
Your inclination is 45 degrees.
45 degrees?
Yeah.
Orbital inclination is 45 degrees, okay. So then if I rotate that, where that plane crosses the equator at, let's say, London.
Yep.
So what does that mean versus if it is 90 degrees out?
Well, we're going to put a number on that so we know.
Okay.
But remember that the Earth is spinning the whole time.
Oh, that makes it hard.
In the orbital plane you're in, your orbit doesn't care that the Earth is spinning. It just knows that there is a single theoretical point that is the center of the Earth's mass, and that's what it's orbiting. And in fact, that the Earth is spinning doesn't matter.
Is this the argument of...
Oh, very good. Look at you.
I've heard you say it before. Argument of perigee?
Yeah, well, I'm coming to that.
Okay, we're not
so
there
almost,
yet. Okay.
Almost. It is the right ascension of the ascending node.
Right ascension of the ascending node.
But let me explain it to you.
Okay, please do.
Okay. Because remember, these terms sound really arcane, but remember what I said. German guy wrote a paper in Latin,
Right.
retranslated into English
Right.
in the Renaissance.
Okay.
Okay, so we have a lot of terms you don't encounter in your daily life, but I'm
Right.
going to translate them to plain English for you.
Okay.
So here's this elliptical orbit. We've inclined it, right? So 45 degrees you pick, so we're going around it. And so we come up to the high point over the pole, and we come back down and we cross the equator again down into the south. In the point where we cross the equator, or the equatorial plane,
Okay.
that's an intersection. Well, if you're Johannes Kepler, you call that a node.
Okay.
Okay. And in fact, you're going from north to south, so we call it a descending node, because we European astronomers know that north is up and
Right.
south is down.
Right.
Totally arbitrary.
Somebody picked that up.
But
Yeah.
we just call it that, descending node. And then it goes down around, towards the South Pole and back up, and we cross the equator again, south to north, ascending node, because we're going up.
Oh, I see. So, do you know how when you were kids and you played in the woods with your friends and you're like exploring places you've never been and you felt like, okay, I'm a little lost,
Yep.
but it's really fun?
Yeah.
We just got there, but you're showing me the new cave we're going to explore. So
Yes. Yeah.
this is great. So the ascending node means when it's going back towards the North Pole.
Yes. From the south, crossing the equatorial plane or the equator,
Okay.
projected out into space.
Okay. So is it the longitude when it's ascending?
Very good.
Okay.
So one of the terms you see nowadays instead of right ascension is longitude. So we want to know where that ascending node is. Is it here, 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 here?
Is it
Right.
over London or is it over
Well,
Ecuador?
London's going by all the time.
Oh yeah, it is.
Right?
Isn't
Remember? And so what we do is we got to
And
reference
London's not
it.
on the equator, so that doesn't.
London's not on the
Yeah.
equator.
Is it in Uganda or is it in Ecuador? Okay, I'm with you.
We want to reference this to some distant fixed location in space instead of the Earth's rotation, because the stuff on the Earth isn't standing still, right? It's rotating.
Right.
And so we just arbitrarily pick some fixed location in space. And we arbitrarily chose the vernal equinox, the first day of spring.
Okay.
Why? Because if you're a guy without GPS and satellites, it's easy to know when the first day of spring is because you can just observe it.
Right.
On the first day of spring, I don't want to explain this. I'll come back to this later.
First day of
it's also
spring,
really
it's
cool.
going to be, yeah, it's when, okay, I'm with you.
All right. And so when you sort of project from the center of the Earth out through the equator, out into space on the first day of spring, it's always lining up with a fixed point in space. And we call that the vernal equinox reference. And when Kepler was doing his thing, it was a star in the constellation of Aries. We call first point in Aries. But you can, it's far enough away from the Earth that it doesn't care where we are in our orbit of the sun or the fact that the
Is it always the same?
No.
Okay, that drifts,
Because
doesn't it?
so here's the axis of the Earth. Pretend my hand is the Earth, And we rotate around our axis, right?
23.5 degrees.
Except we also precess, right? You know that, right? The wobble, the Earth wobbles. So 26,000 years to make a complete wobble.
I didn't know that.
And so it was in Aries during Kepler's time. It's closer to Pisces now, just because of where we are in the wobble.
This is fascinating. So we need a reference frame that we don't have.
Yeah. Well, we're counting on the deep celestial space.
Right.
And so we just choose that arbitrarily as our reference. And so if we want to know the orientation of our orbit, we measure the angle from the first point in Aries, or the vernal equinox, out in the distant stars, angular around to where that ascending node is. And we measure it as an angle.
Okay.
So that's another orbital parameter.
Okay.
I think we're up to 4 now.
Yeah. Yeah.
And then there's
what is that one called? You said it's the right ascension?
Right ascension. Right ascension is rotating from the right, from the vernal equinox reference, to the point where we have an ascending node.
Got it. Okay.
Right ascension of the ascending node.
Right ascension of the ascending node. Okay.
Or the longitude of the ascending node.
Longitude of the ascending node.
Or the argument of the ascending node. Another archaic meaning for that word. Today, you go argument. What are we like? Are we like the stars are fighting? Argument is angle.
I didn't know that.
Yeah, that just was the word that the English used for angle in the 16th century.
So Newton would have used that.
Newton did use that.
Okay.
So now we know where we are, and there's one more thing we don't know about our orbit.
Where we are in it.
No. Well, that too, but about the orbit itself. Remember, we've got this long axis, and we've got the top of that long axis. We know that the plane is here, but how do we know it's not like this or like that?
So how do we know that, to say it for audio purposes, how do we know the clock angle of
Bingo.
The clock angle of the ellipse?
Exactly. So we measure another angle from the ascending node again. What is the argument?
Argument of
apogee.
Apogee. Okay,
you could do the same thing for perigee, doesn't matter. Or apoapsis, which is generic. Perigee's on the Earth. Yeah. And so that's one more angle.
Okay.
Yeah. So now we've got everything. We know the shape and the size. We know if it's tilted, that's the inclination. We know where it resides this away relative to the vernal equinox at any fixed reference. We choose vernal equinox, right ascension of the ascending node. And now we've clocked it for the highest point of that orbit.
Right.
And now we've completely defined the orbit and how it's oriented. And now we're ready for the last thing we don't know, which is where are you at any moment in time? And we call that the true anomaly.
The true anomaly?
Yeah, because anomaly is another word for angle.
Is it really?
So we can say, well, I'm over here. And if you know all of that stuff...
Do you think people listening are asleep now?
But yeah, I think they are. I don't know why you asked this question.
I'm still with you because I don't know this. So we've got what was the first term?
So we had our semi-major axis.
Semi-major axis.
Our eccentricity.
Okay, eccentricity.
Then we had our inclination.
Inclination.
Which is our tilt.
Okay.
Then we had our right ascension of the ascending node.
Right ascension of the ascending node.
Sometimes called the longitude of the ascending node.
Longitude of the ascending node, okay. Fifth term is the...
argument of perigee or argument of apogee, doesn't matter.
Okay.
Just
argument of
say
apogee.
which one.
And that's the clock angle of the ellipse relative. Right. Okay. And then the last one is the...
true anomaly.
True anomaly. I didn't know that, Tory. I'm supposed to know that. I did not know that.
You know it now.
That's pretty good.
And if you know all of that, you can know where the satellite is at any moment in time ever.
But I'll also know where I'm going to be
in the future.
5 years from now?
You do, yes. Assuming that nothing happens to your orbit, drag, whatever, because of other Kepler's laws that tell you how fast you transit through that shaped orbit.
Right.
You always know where you are.
Kepler was a smart guy.
Super smart guy to have come up with all of this literally during the Renaissance.
That's amazing.
1500s.
I was at fall break with my family, and we were at an Airbnb, and I saw Newton's Principia on the shelf.
Oh yeah.
And my
In
son.
Latin.
No, this one was in English.
Oh, okay.
Did he write it in Latin?
Yeah.
Okay, well.
That was the universal language.
This one was in English. And so I saw this thing on the shelf, and I was like, oh, I have access to calculus and differential equations is a thing.
Yeah.
I can just pick this up and understand it, I'm sure. Picked it up, and I was like, man, Newton was a smart guy.
Do you know how old he was when he wrote it?
He was very young, right? It was during a pandemic, wasn't it?
Yes. And which one? I want to say the sweating sickness, but irrelevant.
Yeah.
By the time he was 26, he'd already done the universal laws of gravity and invented calculus, which he only invented to answer another question somebody else had asked him relative to gravity that you couldn't answer without inventing calculus, and a couple of other things.
That's amazing. Yeah, what are we doing?
I don't know.
You're just building rockets and proving their laws.
We're wasting our lives here.
That was great. Thank you for teaching me that.
Oh, you're welcome.
I appreciate that.
Yeah, sorry viewers.
No, not at all. That was great. I think that needs to be out there somewhere.
Yeah.
I'm going to figure out how to, yeah. So if I were to give you a 6-digit number, you could tell me exactly what the orbit looks like and where you are.
Yeah,
and what is
absolutely.
the true anomaly measured in? What is the
angle? It's usually measured in angle.
Okay.
Yeah.
All right. That makes sense.
Relative to the ascending node.
Relative to the ascending
Everything's the ascending node.
node. Okay. That's awesome.
Yeah.
Cool. Thank you.
So my next question is, because I was thinking about when you were doing U.S. Army missile flight testing, OT&E role, and so, I've worked with those guys over the years, and, they're in there seeing how your thing works, and is it suitable for use, and are there quirks and things that we should understand about it, or maybe fix?
Right.
Before we let people, put their lives in its hands.
Right.
That's how I think of it. And I used to do a couple of different things. At one time, I did a job that was called foreign exploitation, which sounds really weird. It's a little bit like orbital parameter terms that are not obvious from their name. But what I was asked to do was to take intelligence gathered by intelligence agencies about Soviet systems and then try and fill in all the blanks. So back engineer how it worked and what it could do, and maybe its weaknesses and strengths, stuff like that. And then later, so kind of similar in a way. And then later, I got to fly foreign military assets.
Wow.
Which as targets for missile defense. So you know what those are, but for our listeners, these are other people's rockets. Don't ask where I got them.
That's amazing.
And they don't come with instructions. So kind of a similar thing. And so I thought, well, what you did in OT&E is kind of like that. You didn't design this thing you're testing.
No.
So you're going to go out and use it and see how it works and what you think about it. What do you think about that? Is that legit?
I think it's fascinating. This is a fascinating thing. And one thing I think about a lot is when you test weapons, which I tested weapons.
Mm-hmm.
I tested a lot of defensive systems. I did test some offensive systems as well. But one of the things that I think is so fascinating is you have humans on Earth. And then at some point, one person tries to hoard wealth or power or whatever, and then naturally politics will arise.
Yep.
And then from politics comes conflict, and then from conflict ends up at some point on down the trail there's kinetic. It's
sadly
it's a very bad thing. But one thing that I think is so fascinating about it is the physics is the same no matter what.
Right.
The tyranny of the rocket equation applies to you.
Oh, yes.
Just like it does to everybody on the Earth.
Everyone equally.
Right. Tsiolkovsky figured it out, but the tyranny of the rocket equation is just true. And so everybody's playing by the same rules, but they're trying to interact with each other. And so this has been happening for as long as there's been conflict. Someone picks up a rock and throws it at someone invents a shield. someone invents a faster rock, maybe a bow and arrow, maybe a sling.
Yeah.
And then pretty soon you work your way up to bullets and gunpowder, and then you go to shape charges, and then you go to reactive armor, and then you go to all these things, and now we're at fiber optic drones.
Yeah.
I think it's fascinating that you've got conflict, human conflict, but somewhere in there, there's a scientist in another country that's looking at the same things that a scientist in this country is looking at. And they're competing with physics. And I just find it to be fascinating. I hate it.
Yeah.
I wish there would be peace on earth and goodwill to all men. But it's just a fascinating thing that we're all bound by the same physics and we all have to play by the same rules. So these things that you got that didn't have instructions, you might not have been able to read an instruction manual about how the thing operates, but you do know the rocket equation.
That's right.
And you could figure out, based on certain chemistry, what the ISP of the propellant was, therefore you could figure out what it could do. I just think that's fascinating. It's a fascinating thing. Yeah, I can imagine that's a very interesting thing for you.
It was super fun. Well, your work looked amazing.
It's pretty. I was able to be a part of some really interesting things. Yeah, and I miss it. I miss it a lot.
Yep.
And I think about it a lot too. And so I can think back on certain days on the test range. The people I work with, I can think back on certain days and like, wow, we figured that thing out that day. It's just a really interesting thing.
It's the coolest feeling, isn't it? So satisfying.
It is, and the idea that you were able to help a soldier come home safely, is an important thing. It's a really important thing.
Well, I think that's worth talking about for a second because you've worked in testing weapons, which is part of developing and fielding them, and me too, but not to hurt anyone.
Right.
This work is about keeping the peace, and what we've learned, sadly, through millennia of human history, that you have to be strong, you have to deter aggression because there's always going to be someone who does not share your values and doesn't feel that way, and they're more than willing to bring those kinetic effects to achieve their goals. And you just have to make the cost too high in order to keep the peace.
When I was a little boy, my dad told me a story about a young man he grew up with that had deformed hands. And people bullied the boy with deformed hands. And Dad said, one day I just had enough, and I fought the bully. I fought the bully behind the school that was making fun of the boy with deformed hands. And I remember thinking, that's fascinating. Like, you would use your own strength to try to defend the weak. And I found that to be a very compelling story as a young man. I was always pretty small physically, but I think it's important for the strong to stand up for the weak, not for their own selfish gain or ambitions, but to help those that can't help themselves. And so I remember when I was working for the Army, I can remember seeing a situation where I won't say this specific conflict, but I remember seeing some imagery of a family, and it was a dad who was pushing his child through a fence to try to, like, they were refugees. It's like, get me out of here because this despot is trying to. And I remember thinking, okay, and we were starting to get involved in that conflict, and I remember thinking, okay, that's why I'm doing it. Because that guy doesn't live in America.
No.
But no nation is perfect, and you can see.
Oh, no, of course not.
Yeah. But the internet has been, if you read, and I do read the comments, and it's an interesting thing hearing people talk about how evil you are because you chose to do something that defends their ability to say on the internet how evil you are. And I was like, okay, that is a choice I made. Also, you have the ability to say what you want, and I think that's important. So.
Well, what an incredible role model you had.
My dad did a great job. Daryl,
I think that explains a lot.
It does, yeah.
Well, I feel the same way. We do this work because it matters, and not just to protect our own. I think some people think of it that way. It's sort of a tribe way of looking at it. I'll protect my family, or I'll protect my nation, and I don't care about others. That's not what our country is about.
No.
And for all our human frailties, because America is a human construct, so it can't be perfect, I feel that our nation has done more for the cause of human dignity than any institution in human history. And if you don't think that's true, you probably don't understand very much about history.
I've been, so up to this point in my life, I've been spending a lot of times doing science, technology, engineering, math. But I've recently started speedrunning the humanities, is what I'm calling it.
Oh, yeah.
So I've been reading a lot about classical education and just learning a lot about philosophy and stuff like that, and trying to come up to speed on history. I started in Persia.
Yeah.
Then I went to Greece, then Rome.
Ancient world, classics,
very
good.
I feel like I cheated myself early on for not researching this stuff earlier, and I wish I had. So I'm trying to catch up. I'm playing catch up.
Well, when you've got all kind of, you can tell me if you agree. All right, let's see. We got more questions here. Oh, here's a good one. So you're an engineer, obviously. We've been talking about that. And, you do all kinds of different stuff, but you've gotten involved in space a lot lately. And here you are in the physically largest rocket factory in the world.
Is this the physically largest?
Over 2 million square feet.
Wow, I didn't know that.
Yeah, well, these are big rockets. It takes a lot of space.
Yeah, yeah.
So if, as an educator in a way, and an engineer and a dad, I wonder, when you think about space, what are the things that you imagine in the future that you find the most exciting?
About space?
Yeah.
It's simple. I look forward to waking up and seeing what the people on the moon are doing. When I was young, we read a book called The Runaway Robot by Lester Del Rey.
Yeah.
It's a classic. And this little boy, I think his name was Paul, he lived on Ganymede with his robot. And his robot ran away, and they were fungus farmers or whatever it is they did. And I just remember thinking that was really interesting, that there are other worlds and people could live there. And I think it makes sense for people to live on the moon. I think it'd be really cool to have a radio telescope on the other side of the moon, the side opposite of Earth, because it'd be shielded from a lot of the RF. Well, I guess we would have lunar satellites at this point. So
we probably would, yeah. We're going to need GPS and comms on the moon.
Yeah, but it would be quieter than here in terms of radio spectrum.
Right.
So I think it'd be really neat to have a telescope on the backside of the moon. But I do just, from a human level, I want to see what the people on the moon are doing today.
Yeah.
I'm excited.
That's super cool. I love that vision. Yeah. I think about that too. Because, here we are on Earth, and, we think about our resources and the finite nature of them, and we try and be more efficient and sustainable and everything. But if that's all we ever do, we will run out someday. Mm-hmm. And yet right there, 3 days from where we're sitting on this platform, our imagination-defying abundance. On the moon, on the near-Earth objects beyond it, we got to go there and develop those and have ordinary people living and working there, just regular folks, because their jobs are there.
Their jobs are there.
Yeah.
So they would do a commute.
Yeah. Or they can live there.
Yeah. Yeah. Well, they would do, maybe it's like an oil rig where, I've had friends
definitely. At first,
they're out on the rig for a while, and then they come back. That'd be pretty interesting. Or they just stay there. That's interesting.
Because you can have a better life there.
Yeah, that's interesting.
All right, we're getting like the high sign. So we got to go to the lightning round.
Okay, let's do it.
They warned you about this?
Yes.
All right.
I remember one, yes.
I'm going to give you an A or B.
Okay.
You got to pick one. Well, you don't have to explain it.
Okay.
Sometimes people pick both.
Okay.
Sometimes they pick a third. It's kind of up to you.
Okay.
But the idea is we're going to kind of blast through them.
Okay, let's do it.
All right, Kirk or Spock?
You gotta go, Kobayashi Maru, you got to go Kirk.
All right,
yeah.
I like it. JFK or Teddy Roosevelt?
Teddy Roosevelt, man in the arena.
Yep, me too. Me too. OT&E or YouTube?
Oh man. I really like learning and exploring on YouTube, but I really loved figuring things out with test and evaluation. I guess the thing is, I would just keep the same curiosity no matter what I'm doing. But if you made me guess, or you made me pick, I'd say YouTube is the right place, obviously, because I have picked.
Yeah. That's understandable, and you're so good at it. You really are.
I appreciate that.
Redstone or Wismer?
Redstone. Yeah, I'd have to say it's green. It's green. You can go out for lunch.
Yes, you can.
Yeah.
It is so remote at Wismer.
Yeah,
oh my gosh.
It's way on out there.
I remember the first time I went out there, I got ordnance trained for safety, and I sit in this room all day long, and there's an EOD guy who's training us, and he's, it's been arranged since 1950s, right?
Oh, yeah.
And so he's like, okay, this weird shaped little thing, that's an initiator, and it's got, 10 ounces, and they'll blow your hand off. And this little thing like a sphere, that's an unexploded cluster bomb. And it just goes on all day long. And we get to the end, and they had like an evaluation, and he was, and I fill it out, and the guy says, you gave our course a negative evaluation. Why? And I said, well, I feel like it was a waste of time. He goes, a waste of time? You could die out there. I go, I understand that. But all you had to say is, if you don't know what it is, don't pick it up.
That's right.
All day long.
There's one place I've been, I think was it Dugway or China Lake, where you can't disturb the turtles.
Yeah.
Because
I think that's Dugway. Yeah.
Yeah, okay, yeah. Because they'll get scared and they'll
China
pee.
Lake has the endangered lizards.
Okay, I haven't been there. The turtles will pee, though, and they have to call the turtle specialist, and he'll come rehydrate the turtles.
Oh, my gosh.
Which is awesome.
Yeah, that's cool. All right, so now we're going to do a rocket.
Okay.
Vulcan or Delta IV Heavy?
Okay. Well, I don't know enough about Vulcan yet.
Oh, well, we're going to fix that.
Yeah, well, I've seen them both launch, and I'll say the Delta IV Heavy was magnificent. However, the Vulcan just worked. Like, they were both great for their own thing. Which one has the most payload?
Vulcan.
Okay, we'll go Vulcan then.
All right. Okay. Laminar or turbulent?
You know the answer is laminar.
It's
got to be laminar.
It is.
Well, what's your
flow.
answer to that question?
So I also love laminar, but turbulent flow, I have a relationship with it.
Okay.
So there was a time when I was doing hypersonic gliders, and we had this big glider, it was like the size of this platform, and we flew it through an aerodynamic regime that really hadn't been flown before. And by regime, I mean a combination of like altitude, density, velocity.
Okay.
And the space shuttle avoided it. We had to fly through it, and we discovered all kinds of like sort of new aerodynamic effects.
Is this where things disassociate?
Yes.
Like compounds
yes.
start cracking?
Yes, yeah. Exactly. And so there was all kinds of learning. So that was super cool. But my glider failed, and so that was not super cool.
It's not cool.
So I have this weird relationship with turbulent.
It has its purposes. It's also beautiful, but in different ways.
And it was a symmetric body flying with like zero yaw, and I had asymmetric conditions on the windward side. I was laminar on the left and turbulent on the right. That's what led to my problems. We never did really understand why.
I don't understand that.
Crazy, huh?
At hypersonic velocities?
Yeah.
I don't understand that.
Yeah. It was weird. All right, Javelin or Hellfire?
Javelin's just so cool to watch. I mean, Javelin's just a really neat missile.
It is super neat.
I mean, it's just really cool. So Hellfire just comes right off the rail screaming.
Yep.
Javelin has a 2-part rocket that uses the same nozzle for both.
Yeah.
That's pretty cool. I just like the servos. I came from the tow days.
Oh, yeah.
The wing and fin clicking, but the Javelin going so smooth. Javelin's pretty neat, but Hellfire's got better range.
And it's different to operate it.
It is.
So I'm jealous because you probably shot both of them. I've only done the trainer on the Javelin.
I've never fired either one of those two.
Oh, you haven't? Oh,
no, I've been a part of the tests, but I've never pulled the trigger.
Well, someday you and I should test one. On the range, working for the government.
Sure, yeah. We fired a Hellfire at Eglin one time, but I wasn't. Strangely, they don't let you just fly in an Apache if you're not a pilot.
Strangely, yeah. All right, last question. And I've been watching your latest series of videos, which inspired this. So And if you don't understand what the first one is, it's okay. You just ask me, I'll tell you, and then you
Okay.
can pick. So what do you think? Aneutronic helium-3 fusion or plain old 235 fission for electrical power?
You said the first one's aneutronic?
Yeah, so you're not familiar with this
I'm not
one?
familiar with aneutronic.
This is one of our really exciting lunar resources, helium-3.
Okay.
So it's a stable isotope of helium, and there's two reasons people get excited. One is it can be used in a refrigeration cycle that reaches very close, like millikelvin, so close to absolute zero for quantum computing applications.
Wow. Okay.
And the other application is a fusion reactor that theoretically would have no leftover neutrons and therefore not have radiation coming off the reactor.
Really?
Or at least less.
No ionizing radiation coming out.
Right.
Okay, that sounds fascinating.
That sounds pretty cool, huh?
It does.
And it's super rare on Earth because we have an atmosphere,
Right.
and pretty much all the helium-3 we get is, in a way, recycled nuclear weapons. It's a decay product of tritium.
You're over my head. I don't know. So I can't pick that one.
Okay, so there's that one, but
Yeah.
on the moon it's abundant because it comes with solar
Is
wind.
this the cislunar,
It's the cislunar
economy
stuff.
you've been talking
Yeah,
about?
yeah, that's one of the resources we would gather from the moon.
Okay.
It's just laying in the regolith, blown there by the sun.
You can mine it.
Yeah.
That's pretty cool. I need to read about this. It's called aneutronic.
Helium-3 fusion, which would be aneutronic.
Okay.
Aneutronic, like antibiotic or,
Right.
So no extra neutrons, theoretically.
Okay. I need to read about that. There's one I would add to your list
Okay.
that I think is interesting. Thorium.
Oh yeah, thorium.
I think that would be interesting because it's already molten as I understand it.
Yes.
I don't know a lot about it.
So thorium reactors, salt reactors, those kind of
It
cycles.
can't melt down because it's already melted down.
Exactly.
I think that's fascinating.
Me too.
Pretty excited about uranium though, and the microreactors.
Really, it's pretally cool.
Yeah, I think
These
we're
now
seeing.
small modular reactors.
I think we're seeing a nuclear renaissance right now.
I think so too.
Yeah. Yeah. Well, this was fun.
This was super fun.
Yeah. Thank you very much for having me.
Thank you for doing it.
Yeah.
Appreciate it.
Thanks, Tori.